Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 2nd, 2025, about 2 days ago. This paper shows a self-driven reinforcement learning method that, without any gold labels, boosts pass at 1 by up to plus 140.7% on AIME25, plus 36.2% on MMLU STEM, and plus 19.6% on GPQA Diamond, nearly matching gold label training. The paper is titled RESTRAIN, From Spurious Votes to Signal Self-Driven RL with Self-Penalization, and the implications for model training are quite significant. It converts unlabeled rollouts into learning signals with self-penalization, integrates into grouped relative policy optimization, and avoids the collapse seen with majority vote schemes. Alright, the introduction set the motivation for label-free reinforcement learning. Figure 1 presents bar charts that compare methods across math and science benchmarks, showing that self-penalized training beats test-time reinforcement learning baselines. The top panels compare pass at 1 for QN3-4B base and OctoThinker hybrid 8B base, where the method nearly matches gold label GRPO and even surpasses it on MMLU STEM and GPQA Diamond. The bottom panels report test time training on AMC, AIME24, and Math 500, with clear gains over TTRL and ETMR. Alright, the previous figure highlighted headline gains. Figure 2 now probes why majority voting misleads, showing pass at 64 far above the majority answer correct ratio across different majority sizes. The left panel for QN3-4B base shows a wide gap, which means correct answers often do not win the vote when agreement is small. The right panel for OctoThinker hybrid 8B base shows the same pattern, so reliance on hard majorities risks reinforcing spurious modes. Well, Figure 2 showed that hard majorities can mislead. Figure 3 presents the pipeline, which routes rollouts through a consistency check, and then applies 3 self-penalizing components. The pseudo-label weighting block treats every distinct answer as a candidate, and weights its loss by a shaped frequency, so promising minorities still count. The negative rollout penalization block kicks in when the majority falls below a threshold kappa, zeroing rewards and subtracting a negative advantage offset. The prompt weighting block scales updates by reliability from a reference model, and the final loss combines prompt and label weights. So, the pipeline was clear. This panel shows the core objective, which defines the restrain loss as a prompt reliability weight times a weighted sum over pseudo-labels, each fed through a GRPO-style loss. The GRPO term uses a clipped importance ratio to keep updates stable, and adds a KL penalty that tethers the policy to a reference. The advantage shaping encodes self-penalization so low consensus prompts reduce or reverse rewards, while promising reasoning chains remain reinforced. So the objective was defined. Table 1 reports the main results across 6 benchmarks. For QN3-4B base, restrain averages 51.0 versus TTRL at 42.2, nearly matching GRPO at 51.4, with standout jumps on MMLU STEM at 80.9 versus 59.4, and GPQA Diamond at 40.2 versus 33.6. AIME25 rises to 17.9 from 8.3, which is about 116% higher. For OctoThinker hybrid 8B base, the average reaches 35.8 versus 30.6, and AIME25 climbs to 6.5 from 2.7, roughly 140% higher. So Table 4 breaks down which parts mattered most. The full method averages 51, while removing pseudo-label weighting drops the average to about 37, which signals rapid collapse because the training signal loses its smoothing effect. Removing negative rollout penalization lowers the average to about 42, and removing prompt-level weighting yields about 48. The largest single-column gap appears on MMLU, where 81 falls to about 59 without pseudo-label weighting. Alright, 2 takeaways stand out. Self-penalized reinforcement learning that uses the full rollout distribution avoids majority vote collapse, and it reaches near gold label performance while using no labels. The broader implication is practical self-improvement at scale, cutting annotation costs and generalizing across domains. Thanks for spending time with me. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.